Welcome, students. We are going to discuss multiplicative functions. So we'll start with discussing one special kind of multiplicative function, which is the Euler phi function. Before we go there, let's define what is a multiplicative function. Multiplicative functions are special class of arithmetic functions. So what are arithmetic functions? So arithmetic functions are functions which are defined for all positive integers. So the domain of this function is all natural numbers. So your natural numbers is starting from 1, 2. So this gives you all the positive integers. 2 what? 2 generally is considered C for the properties of number theoretic perspective. Now a function, arithmetic function is called multiplicative if m and n are coprime. If you take two positive integers which are coprime, then f of mn is f of m times f of n. Then such a function is called multiplicative. A completely multiplicative function is a function such that f of mn, m times n, is f of m times f of n without having the condition of m and n being coprime. So we'll study Euler phi function, which is multiplicative. So first, let's recall what is Euler phi function. So again, Euler phi function is defined for positive integer. Why? Well, it's also arithmetic function. So Euler phi function phi of n is defined to be number of positive integers not exceeding n that are relatively prime to n. So what does it mean? It means, so if I want to write down phi of n, phi of n is all those x belonging to n such that, first of all, x should not exceed n, and x and n are coprime. I mean, this is not really needed when we say x is natural number. Okay. So this is your phi of n. Let's look at few examples. What is phi of 1? Phi of 1 is 1. Phi of 2 is 1. Phi of 3 is 1 and 2. So phi of 3 is 2. So here by this we mean the size of this set. Okay. Phi of 4 is 1. You have to count the size, so it's basically size of 1 and then 3, which is 2. Phi of 5 is 4. Phi of 6, let's see what are the numbers which are coprime to 6 and less than 6, less than equal to 6. So 1 is okay, 1 is possible, 2 is not, 3 is not, 4 is not, 5. So phi of 6 is 2. And phi of 7 is a prime. So everything less than or equal to 7 is going to be coprime with 7. So it's going to be 7 minus 1, which is 6, right? Everything less than 7 is coprime to 7. By less than, I mean I'm only considering the positive integers. So we'll soon see the multiplicative structure. So Let f be, before that, let's see the properties which are applicable to all the multiplicative functions. One of them is the following. Let f be a multiplicative function and n be p1 to the power a1 dot 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 ps to the power as is the prime power factorization of n. Then f of n is f of p1 to the power an blah 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 ps to the power as. So recall, or otherwise, from fundamental theorem of arithmetic, if you're given a natural number, you can write it as p1 to the power a1, p1 to the p to the power a2 dot 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 ps to the power as, where these ai's are what? Ai's are greater than equal to 1. Yeah. So this is a prime factorization of n, and multiplicative, if f is multiplicative, it distributes over in the following way. So let's see the proof of this. We will prove it using induction. So induction on what? So induction on number of distinct primes. Say call it k. Number of distinct primes in their prime factorization. So if for k equals to 1, we have n equals to p1 to the power a1, then f of n is same as f of p1 to the power a1, and this is, of course, this is obviously true, so this is trivially true. Now the induction step. So let's write induction hypothesis. Assume it true for k. What does it mean? That means if n equals to p1 to the power a1 dot 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 pk to the power ak, then f of n is f of p1 to the power a1, f of pk to the power ak. So now we need to prove for k plus 1. Yeah, this will complete our induction. So if n equals to p1 to the power k, pk to the power ak and pk plus 1 to the power ak, then note that these are primes. So we have p1 a1 pk ak multiplied together, this, and pk plus 1 ak plus 1 are relatively coprime, right? So this implies, and since f is multiplicative, this gives f of p1 pk times pk plus 1. This will split as f of p1 a1 pk ak times f of pk plus 1 ak plus to the power ak plus 1. Now this splitting happened because of the multiplicative function, and now because of induction hypothesis, that is equal to f of p1 a1 f of p2 to the power a2 dot 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 f of pk to the power ak times f of pk plus 1 to the power ak plus 1. So you have completed the induction step, and therefore this is true. All right, so this is about multiplicative function in general. Let's come back to the Euler phi function. So now property of Euler phi function, if p is prime, then phi of p is p minus 1. And conversely, if p is a positive integer with phi of p equals to p minus 1, then p is prime. So let's prove both ways. So let's start with the first part. If p is prime, then only divisors of p are 1 and p itself. Now what does it mean? That means 1 to p minus 1 have no divisor which divide p. That means that is x and p are coprime if x is between 1 and p minus 1. Therefore, phi of p is equal to p minus 1. Conversely, if phi of p equals to p minus 1, we want to show that p is prime. So we'll prove by contradiction, or you could have proved it by contrapositive, but we'll prove it by contradiction. So assume p is not prime. This implies p equals to ab, where, so if p is not prime, it means p is composite, right? So this p equals to ab, or the other case is p is 1, right? Where a is less than 1, greater than 1, less than p, and we have or p equals to 1. Now let's take care of p equals to 1. So if p is 1, phi of p is 1, which is not equal to 0, which is p minus 1. So p can't be 1. Now if p equals to ab, then a is an integer less than p, which is not co-prime with p, right? With a and p not equal to 1. It's actually a, but so therefore phi of p will be less than p minus 1, yeah, which contradicts what is given or our assumption. Hence the result, right? So now let's move on to the next problem. So let p be a prime and a be a positive integer. Then phi of p to the power a is p to the power a minus p to the power a minus 1. So first, let's see what does phi of p to the a. So what we'll do is the following. We will count the integers. So let's count the following integers. The positive integers, which are less than or equal to p to the power a, and are not coprime with p to the power a, are precisely factors, are precisely the multiples of p which do not exceed p to the power a. So the strategy here is to count the ones which are not coprime to p and exclude them from the total set. They are of form I times p, because they are multiples of p, so I has to be from 1 all the way until p minus 1, right? So these are all which are multiples of p and do not exceed. And there are how many of these? So there are exactly, all these choices are okay. So they're exactly p to the power a minus 1 of these. So this means what? This means remove all of them. This implies there are exactly p to the power a, and then you remove the ones which are co-prime to it. Sorry, which are, so remove the ones which are not co-prime to p to the power a. Exactly p to the power a minus p to the power a minus 1 of these integers, again, which qualify to be phi, or which qualify to be relatively coprime with p to the power a. So let me write that properly. So they're exactly p to the power a minus p to the power a minus 1 of these integers, which are less than or equal to p to the power a and relatively coprime to or relatively prime. Yeah. So you use either one of them, are either coprime or relatively prime. Or relatively prime to p to the power a. So therefore we get phi of p to the power a is phi of p to the power, sorry, p of p to the power a is p to the power a minus p to the power a minus 1. So all this is going to help us in the algorithmics of things. But before that, let's look at an example. So now there are some numbers for which we can find phi of, say, phi of 5 to the power 10. It's such a big number if you have to go and find out all the values uh, or all the integers which are co-prime to 5 to the power 10. But thanks to this formula, we have that is going to be 5 to the power 10 minus 5 to the power 9. Okay. So now comes the part where we prove that phi is an arithmetic, sorry, phi is a multiplicative function. So let m and n be relatively prime positive integers. Then we want to show that phi of m times n is phi of mn. So we'll do the following. We will list the numbers mn in the following order in a rectangular array. So we have 1, 2, 3, 4, dot, 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 r, dot, 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 m. Then you have m plus 1, m plus 2, m plus 3, m plus r, then you have 2m. Similarly, m 2m plus 1, 2m plus 2, 2m plus 3, 2m plus r, 3m. Then again, we'll keep listing this. We'll have n minus 1 times m plus 1, n minus 1 times m plus 2, n minus m, n minus 1 times m plus n, which is going to be mn. So let's consider the following rectangular array. Yeah, so I should list this element as well. So this is going to be n minus 1 times n. And now what I'm looking for is phi of mn. We want to find out what is phi of mn. Okay. Now, suppose this r is such that, suppose r is a positive integer, not exceeding n, m with m and r greater than 1. So let's say that is d, which is greater than 1. So this means that none of these are going to be what? So this implies none of elements in the row r m plus r n minus m plus r are relatively prime to r. None of these elements in the row are relatively prime to m. Yeah, so none of these elements are relatively prime to m, and hence will not contribute to what? Hence will not contribute to phi of mn, right? Because phi of mn is, so are relatively prime. None of these are relatively prime to m, and hence are not relatively prime to mn, right? Because they will share a factor with m, and consequently they will share a factor with mn. So what are we looking for? So consequently, so we should look for, we need to look at rth row if m and r are relatively coprime, right? Those for sure are the only ones that have a chance to show up in the integers which are coprime with mn. Okay, so how many of these are there? So, and there are, how many of them? There are phi of m of these rows. So now consider a row. So these are the rows. So now consider a row R are such that what? Such that m and r equals to 1. Now in this row, this contains how many elements? So this contains r m plus r dot 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 n minus 1 times m plus r has n elements in it. And all these are relatively prime with m. Right? Now, out of these, there are phi of n elements relatively prime with n. Why is that? If you take n consecutive integers, positive integers, then you can find phi n of them in this consecutive integers, which are relatively prime with n. So there are phi of n relatively prime integers with n. Now note that these are also coprime with m. So these phi of n integers, so these phi of n integers are also coprime with these phi of n integers, are also coprime with m. So therefore, what do we get? they are relatively prime. They are relatively prime with Mn. So what is our counting goes? So the counting goes, there are phi of m rows, and in all which are relatively prime with n, and out of those rows, for each row you will have phi of n which are relatively prime with n. So the total number is therefore phi of mn. This was our original thing to count. We found out that you get phi of m rows which are relatively, so number of rows which are relatively coprime with n, and in that row there are phi n of them which are relatively prime with n, and together they are relatively coprime with mn. So now we have basically shown that phi is a multiplicative function. Now, once phi is a multiplicative function, we have the following algorithm to compute phi of n. So let n be p1 to the power a1, blah, 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 ps to the power as, be the prime factorization of n, then phi of n is this guy. So what have we shown, first of all? So phi is multiplicative. That means phi of n equals to phi of p1 to the power a1, ps to the power as. Now, that is just an expression. We haven't used the multiplicativeness yet. So let's use the multiplicative property of the function. That is going to be phi of p1 to the power a1, ps to the power as. Now, we already know what is the formula for this. It is going to be p1 to the power a1 minus p1 to the power a1 minus 1 dot dot dot, for similarly for the other parts, and the last one would be ps to the power as minus ps to the power as minus 1. So now out of this, let's take from the first part p1 common. So if I take p1 common, what do I get? I get p1 to the power a1 common. I get 1 for the first part. Second part we have to write as 1 by, there's 1 less, right? So we can write it as 1 by p1. Similarly, we can take ps common from the last one, 1 upon 1 minus ps. Now pull out all these guys up in the front, so you get p1 to the power a1, ps to the power as, 1 minus 1 by p1, 1 minus 1 by, and this is your n, right? So you have proved the following result, which is an easy way of computing the Euler p function. Okay, so let's look at an example. So we used this when we were p of 100. So we use this when we're doing what are the last 2 digits. So let's compute this. So first thing is to find out the prime factorization. So prime factorization of this is going to be 100 is 5 square, so 4 times 25, so 2 square times 5 square. Now this is going to be 100, so this is going to be 100 times 1 minus half, 1 minus 1/5. Yeah, following this result here. So we get 100 times half times 4/5. That is going to be 4/5. So you have 100 times 4, 400 divided by 10, which is 40. Now there are a few more results, a few more problems. First problem is if n is greater than or equal to 3 is a positive integer, then phi of n is always even. Yeah, so that can be seen easily by the following. You can, if n is greater than or equal to 3, then either you can consider that it has power of 2 in it, and then you look at the appropriate power of 2, or it's basically if it is a prime, then p minus 1, the odd, then it has to be an odd prime, and any odd prime is basically going to be give you that p minus 1 for that prime would be even. So let's prove this. So I'm going to prove it here. So proof of what? That if n is greater than or equal to 3 is a positive integer, then phi of n is even. So consider the prime factorization. Consider prime power factorization. N. So what do we have? We have n equals to p1 to the power a1, ps to the power as. Now p is multiplicative, so we get p of n equals to p of, so one of the various forms, one of the forms can be p1 a1 minus 1 times p1 minus 1 ps as minus 1 times ps minus 1. So this is one of the forms of the previous factorization. Now clearly, if p is an odd prime, or pi for some I is a odd prime, pi is an odd prime for some I, then what? Then pi minus 1 is even. This implies what? Phi of n is even. So case 2, none of pi is an odd prime. So if none of them is an odd prime, then n, the only even prime is n equals to 2 to the power some number, say k, for some k. Now since n is greater than equal to 3, this implies k is greater than equal to 2, right? So in that case, we get phi of n is phi of 2 to the power k, which is going to be 2 to the power k minus 1 times 2 minus 1, which is 1, which is even since k minus 1 is greater than equal to 1, right? So it has factor of 2. So therefore, it proves your result. All right, so now these are the few interesting results which we need to show, which we'll work on in the office hours. Thank you for your attention.